In this video, we're going to learn how to analyze the graph of a rational function. Now, this is part one in a series of 2 videos going over how to analyze the graph of a rational function. So after you watch this video, please go watch part 2. So when you're analyzing the graph of a function, you find a bunch of things. First, you'll simplify whatever function you have by factoring it and putting it in lowest terms. And then you'll find its domain, which helps you graph and know which values you're going to plug in. Then you'll find the intercepts, the x and y intercepts of your graph, followed by finding any vertical asymptotes the graph may have, and horizontal or oblique asymptotes if there are any. And then we'll use the fact that we know where it's undefined in its domain and where it's 0 in its numerator as well to split up our interval to have different sections where we can determine if the graph is above or below the x-axis. And then we can use that information to analyze its behavior near each asymptote, and then we can graph it. And it does seem like a good bit because we are doing a good bit, but I promise that it flows through all this information very smoothly. So the first thing you're always going to do is factor your numerator and denominator for a rational function. So looking at this problem, I have difference of squares in my denominator. So what I'm going to do is rewrite this as x minus 1 over x plus 2 times x minus 2. Now, before you put it in lowest terms, you're going to use this form that's factored to determine the domain of your rational function. That is just setting each factor in your denominator equal to 0. And we can see here that the left factor gives me negative 2, and the right factor would give me positive 2. So those two particular x values would create a 0 in the denominator of this function. So I'm going to write its domain. I'll say that x is any real number as long as it does not equal negative 2 or positive 2. So that's how you determine its domain. Now, once you've determined the domain, now you cancel out any factors that you can. In this case, no factors cancel out. We are done. Next, we locate any intercepts of the graph. The intercepts would be, for the y-intercept, plug it in 0 for x. Now, since 0 is on the domain, I can easily plug that in, and when I do, I get negative 1 over negative 4, which is 1/4. So my y-intercept would be 0, 1/4. So on my graph, what I can do is put a point at 0, 1/4 to help me graph later. Next, to find the x-intercepts, you set the numerator equal to 0. When you set the numerator equal to 0, you'll get 1, because x minus 1 equals 0 is 1. So we have an x-intercept at 1, 0. The reason why we just set the numerator equal to 0, because you're setting y equal to 0, which would be this r of x. And the only thing that makes a fraction equal to 0 is if the numerator is 0. So that's why we just check the numerator. So we have an x-intercept at 1, 0. So I can put another point on my graph. And if you want to know how it behaves around that point, what you can do is plug 1 into your formula, but in every factor besides the x minus 1. And whatever formula you get, that's how it behaves at that x-intercept. So if I were to plug in 0 everywhere besides x minus 1, I would get x minus 1 over 1 plus 2 over 1 minus 2. So I would get x minus 1 over 3 times negative 1, which would transfer into negative 1/3 x minus 1. The reason why that's important, it tells me that negative 1/3 is in front of this factor, be a slope of negative 1/3 as I go through that point. So if I had to guess how this was going to interact with this spot, I would go through it at a very shallow slope, but negative. It's going to help me out graph later. Now that you found all of your intercepts, let's determine the vertical asymptotes, which is after you simplified it, each factor in your denominator set equal to 0 represents a vertical asymptote. So in this case, I have a vertical asymptote at x equals negative 2 and x equals 2. So in my graph, I have two vertical lines at 2 and negative 2. where my graph is undefined, but I'll also see the graph bend and follow these lines later on. So those are my vertical asymptotes. Then I'll determine my horizontal or oblique asymptotes. Now look at this problem, since the power is bigger than the denominator, this is a proper rational function. So I'll have a horizontal asymptote at y equals 0. So I'll draw that in as well. Next thing you want to determine is if there are any points that intersect with that particular asymptote and where. Now we can already see that the x-intercept, but the way you would typically figure this out is you would take your function and set it equal to your horizontal asymptote, which would be 0, and solve. So in this case, we would just get x minus 1 is equal to 0 whenever I multiply each side by x squared minus 4. And I'll end up with x equals 1, which is exactly where we expected it to intersect. So cool. That's the only time we ever touch that horizontal asymptote. Vertical asymptotes, you never intersect. That's typically where your function is undefined, so you shouldn't worry about any intersection points on a vertical asymptote. Next up is once you determined these spots, we'll use the zeros from the numerator and denominator to split up our x-axis into intervals. So if I think of this as my x-axis, I'll split up my interval at -2, which would be a 0 in my denominator, 1, which was a 0 in my numerator, and 2, which was a 0 in my denominator. So what this means is that I'll go from -infinity to -2. I'll go from -2 to 1, from 1 to 2, and from 2 to infinity. Oop, not 8, but infinity. So I've split up the entire number line into 4 sections. And the way I determine its behavior in each of these sections, whether it's above or below the x-axis, is I just pick a number within it. So in my first section, I know that -3 is within that section. And in the next interval, I can tell it 0's in that interval, so I'm going to pick that number. Between 1 and 2, I have 3 halves, or 1.5, and after 2, I can pick 3. The way you determine if it's above or below the x-axis is you plug that number into the function. So I'll plug in -3 into my function. And when you do so, you'll get -4 over 5, which is -0.8. Then I'll do the same thing with 0. I'll plug that in. I'll get 1/4, which I already found earlier. I'll plug in 3 halves. Now this one's a little harder to do just in your head, so you could just use a calculator, but to help you out, that's -2/7. And then I'll plug in 3, and I'll get 0.4. So what this tells me is if it's negative, it's below the x-axis. And if it's positive, like you're seeing here, the next one, it's above the x-axis. Negative means below the x-axis. Positive is above the x-axis. So knowing this, when I go to draw later on, when I plot the points here, -3 for x and -0.8 for y, I'll know that the entire graph will stay below the x-axis the entire time for that interval. Same thing here. The 0.014, that spot of the graph on that interval is always above the x-axis. For this next point, 3 halves, comma, -2/7. That point and every other point within that interval is below the x-axis. And lastly, when I plot the point 3.4, that will remain above the x-axis the entire time. So let me go plot these points. So -3, -0.8, 0.1/4, which I already have, 3 halves, -2/7, so just below the x-axis, and then 3.4. So 3 and 0.4. Now the reason why it's important here to know if it's above or below is this section that goes from negative infinity to this green line, -2, it's always below, but it will follow these asymptotes. So the behavior near each asymptote is that it'll flatten out against this one and then flatten out against the other one, but remaining below the x-axis the entire time. When I go from -2 to 1, I'm always above the x-axis. So knowing that, as I go through this point, I'll follow that green asymptote upwards and remain above the x-axis the entire time, only crossing over at 1, where then I'll be below the x-axis. So for the next intercept, I'll be following it downwards. And where this came into play is that this slope right here is a -1/3, right around that spot. And lastly, for 3.4, 3, 0.4, it's above the x-axis, so I know it goes up the green axis on this side and flattens out against the purple, because that's the horizontal asymptote, which only intersects at x = 1, so I know it won't cross again. And that's how you can analyze and graph a function. The last step's always graph, but I kind of just do it as I go along. Let's try this out with another example. So here I have x² - 1 over x. So I want to start by factoring this, which will be x + 1 times x - 1 over x. The only factor in my denominator is x, so my only number I can't plug in is x = 0. So its domain is all real numbers x, such that x does not equal 0. And we'll see here it's already in lowest terms because nothing cancels out. And its intercepts for the graph, I can't plug in 0 to get the y-intercept because it's not my domain, so there are no y-intercepts. And for the x-intercepts, we set it equal to 0, which means set each factor in my numerator equal to 0, giving me 2 x-intercepts at -1, 0, and 1, 0. And if you want to know the slope at each of these points, just plug in -1 into all factors besides x + 1, because that's where it came from, give you -2 over -1, which is +2. So it would have a +2 slope there. So I'll just put m = 2 so you can understand what type of slope it has. And if I plug in 1 everywhere besides x - 1, you'll get 2 over 1, which is also a slope of 2. So I'll have a slope of 2 at each of those spots. So just keep that in mind when we go to graph later. Now we'll see here when we're looking for our vertical asymptotes, there's only one variable down there, so I only have one vertical asymptote at x = 0. And let me plot these points in these asymptotes as well. So there are my x-intercepts, and here's my vertical asymptote. Along the y-axis, x = 0. And then I'll find my horizontal or oblique asymptote. Now the degree difference here is 1, so I'll have to use long division, polynomial long division, to find my horizontal asymptote. So x² + 0x - 1. And how many times does x go into x²? X times. So x times x is x². Subtract that away. And I'll be left with 0, 0, bring down the -1. And since x can't go into -1, since its degree is higher, that -1 just ends up being the remainder. So my horizontal asymptote, or rather, I should use the word oblique, since this is a line with just x, asymptote, is y = x. So I'll have a line of slope 1 as my oblique asymptote. Now, if you want to figure out if it ever crosses that line, you set your function x² - 1 over x equal to your oblique asymptote and solve. Multiply each side by x, I'll get x² - 1 equals x². Subtract x², and you'll get -1 = 0. There's no solution there, so it just never intersects your oblique asymptote. So no line should ever be on that line. Now we'll break up our interval. So the spots that make the numerator and the denominator 0 are at -1, 0, and 1. So the intervals are -infinity to -1, -1 to 0, 0 to 1, and 1 to infinity. In the first interval, to pick a number, we'll pick -2, then we'll pick -1/2, then we'll pick 1/2, that's between 0 and 1, and 2, that's between 1 and infinity. And we'll just plug these in to figure out the value at each of these. So plug it in -2, you'll get 4 minus 1 over -2, so -3/2. Plug it in -1/2 in for x, you'll get the fraction +3/2. Plug in 1/2, you'll get the fraction -3/2. And then plug it in 2, you'll get the fraction +3/2. So negative means below the x-axis, positive means above, negative means below, positive means above. So we're below, above, below, above. So we're going to plot the points -2, comma -3/2, -1/2, comma +3/2, 1/2, comma -3/2, and 2, comma +3/2. So -2, -3/2, so about right here. 1/2, -1/2, comma +3/2, so about right there. 1/2, comma -3/2, and 2, comma 3/2. You can kind of already see how this graph is going to be shaped. But now that we've plotted those points, we can see here that from -infinity up to the x-axis, we're below the whole time. So it's going to follow this horizontal axis, hit this point, then after -1, it goes above the x-axis and stays above. So it'll just follow the vertical asymptote. And same thing here, from 0 to 1, it's below the whole time. So I follow my green asymptote up until that point at 1. Then after 1, it becomes above. And then I'll just go through the other point I found and follow my oblique asymptote. So I'll have a graph that looks like this based on the evidence I saw. And the reason why this is so definitive is the spots that make it 0, which is the numerator, undefined, are the only spots that would make it 0 undefined. So everything in between is either going to be always positive or always negative. And let's address this last example. So here we're going to first factor if we can. I'm noticing here x to the 4th plus 1 is a sum of squares. So there's no way to actually factor that first rational function. So it actually just stays exactly the same. Which means, looking at this, the denominator, its only factor is x. So the domain is x is all real numbers such that x does not equal 0. Just leave that 1 out, which again leads to a very similar answer we saw before. There are no y-intercepts now. And the x-intercepts, there are none either, because if I try to solve this, for x-intercepts, you'll get x to the 4th equals -1, which would lead to an imaginary solution. So there's no real number that works out for the x-intercepts. So it'll never cross the y or the x-axis. Next, we'll find those vertical asymptotes. There will be only one. It'll be at x squared. So my one vertical asymptote, it's at x equals 0. When you set x equal to 0, that's my one vertical asymptote. And then looking for oblique asymptotes or horizontal ones, I notice that the power up top is bigger than the one in the denominator. So I'm going to have to use polynomial long division again, just like I did over here. So I'll have x squared going into x to the 4th plus 1, and I'm put little placeholders for all the missing terms. And I'll notice that how many times does x squared go into x to the 4th? X squared times. So x squared times x squared is x to the 4th. Subtract that away and I get 0, and then I would just, the only number that would come down next would be 1 since everything else is 0, and x squared can't go into 1. So my only asymptote would be y equals x squared, but that's not an oblique asymptote. So if I were to ask the question, is there a horizontal or oblique asymptote, I would say there is none. But what I can say is that it's going to behave like y equals 0. So even though there's none, I'm going to plot this graph of, y equals x squared. I'm going to plot that graph because it's still going to follow that graph. It just doesn't count as a horizontal or oblique asymptote. So graphing the function y equals x squared. And all I'm doing is just taking this x value and squaring it to get these points. This parabola kind of acts like an asymptote for me. My graph will behave like this graph for large values of x. So next up, I can only split my graph into two different sections because there's only one real zero I get, which is 0. So my intervals are negative infinity to 0, and then 0 to infinity. So I'll just pick negative 1 and 1. R of negative 1 will give me 2 when I plug that in. I'll get 1 plus 1 over 1, which will be 2. And R of 1 would be the same exact thing, also 2. So since they're positive, it'll always be above the x-axis the entire time. So it's a non-negative function. And I'm going to plot the points negative 1, 2, and 1, 2. So negative 1, 2, and 1, 2. And when I go to graph it, since I know it's always above, I'll follow my purple parabola. I'll hit this point, and then I'll curve up and follow my vertical asymptote. Still above, I'll go down my vertical asymptote, hit that point, and curve back up and follow my parabola and behavior function. So you'll kind of get these two little loops. Now, I know it was a lot, so take your time and please rewatch certain parts again if you need to see it broken down some more. And if you have a note card, I would write this down to keep it handy for future. So I'll see you in part 2, but that is how you analyze the graph of a rational function.